Welcome back. In our previous video, we introduced proxy variables and measurement error, and we ended with a challenging problem where we were trying to decide which of multiple proxies that are correlated with each other should we choose when deciding to try to correct for this omitted variable bias that we know is present in our model. And we're kind of left in a bad situation where if we include all the proxies, there's going to be problems with multicollinearity. And if we don't include any proxies, then we have this omitted variable bias. So today I'll introduce a method called principal components analysis, or PCA, which is designed to reduce the redundancy in these multiple proxy variables. Instead of making a potentially arbitrary decision about which variable to keep, PCA automatically selects the variables in a particular way, so that what we're left with is a single variable that combines all of the information from the set of variables. However, there are no free lunches, and we'll talk about some of the limitations of PCA as well. If you've taken a course on machine learning, you might have already come across PCA as a technique for what they call dimensionality reduction. And what this means is we're trying to figure out how to compress our data set by removing any redundancies. The intuition is that if I have three variables that more or less all contain the same information, why don't I just discard those redundancies and have one variable that can take the place of all three? And when we want to reduce the dimensionality, there's two ways that we'll talk about in this mini-series to do it. One is called PCA, like I was saying, and the other is factor analysis, which I briefly touched on in the introductory video in this series. And we're going to talk about PCA in this video. So let's say that we have an n by j matrix of data, and we'll label that M. Implicitly, this is called M because it's measurements. And we can decompose M into two different matrices, an n by j matrix and a j by j matrix. We'll call the n by j matrix theta and the j by j matrix lambda. And if you've taken linear algebra, this is a way to obtain the eigenvalues of M. So lambda are all the eigenvectors, and then theta is going to be an orthogonal matrix, meaning that all of the columns of theta are going to be independent of one another or orthogonal of each other. Again, if you've taken a linear algebra course, you likely covered orthogonal bases or orthonormal bases. This is the same type of idea. So the information in lambda basically tells us by how much do we need to rotate each of the columns in theta to get back to our original M. And if M were already orthogonal, then we would just have the identity matrix for lambda, and then theta would just be the original M. And there's a whole linear algebra literature on how to obtain the eigenvalues. There's something called the singular value decomposition. We're not going to talk about any of that in this video. Just know that there's a way to decompose M so that we can obtain the eigenvectors and an orthogonalized matrix theta. So how does all of this linear algebra actually help us with dimensionality reduction? Well, basically what the eigenvectors are going to tell us is which dimension of M is most important in terms of preserving the variation in M. So the eigenvectors that are largest in magnitude are going to be the dimensions of M that have the greatest variance. I should have said M here and not theta. And so we say that we select the first k principal components of M, and that's going to be how we reduce our data. So you can think of it as the 80-20 rule applied to variation preservation. So the idea is, well, I can preserve 80% of the variation by discarding 20% of the data, and that can be like a better trade-off in terms of if I need to store the data in some way, or if I need to choose which proxy variable to include in my model. And so what we do is we just basically throw away columns of M that are redundant. And so that's going to give us something called M tilde. So M tilde is just going to be a subset of this eigenvector and the orthogonalized basis matrix. And so with these two together, we still have our n by j back again, but we're compressing it by throwing away some of the information that is most likely to be redundant. So we can write it down as our original m is our m tilde plus epsilon, where epsilon is just the stuff that we threw away. So let's just go through graphically how we can do this. So let's say that we have two x variables, x1 and x2, and as you can see, they're correlated. In this case, they're positively correlated, and we can obtain the principal components by doing this eigenvalue decomposition. So these are basically the two eigenvectors. And what we're doing is we're trying to find in which direction is the greatest variation of this data cloud. And that's going to be our PC1. And then PC2 is just going to be orthogonal to that. So what is the remaining variation that's orthogonal to PC1? So these two vectors, they encode the information that we would need to rotate this data into a new basis, where that new basis is orthogonal. So how do we do that? Well, we just basically align PC1 with our x-axis. So our new x-axis is not x1 anymore, it's PC1. And then our new y-axis is just going to be orthogonal to PC1. So we've rotated our data, and then where does the dimensionality reduction part come in? Well, now I'm just going to only use PC1 as my variable. And so the epsilon is just whatever these deviations are between these very light red dots and the solid blue dots. So we're basically projecting the data onto the PC1 axis, and then we're just going to use PC1 for our later data analysis. So that is a little bit about dimensionality reduction and principal components analysis. The things to remember about PCA is that, one, it finds the principal component in terms of the variance that's maximized. So the idea is that I choose the principal component such that I can maximize the total variation. That might be useful for us, but it may not be, depending on what we want to do with the principal component. And then the second thing is that we're treating all of the observations that go into that PCA as having not been measured with error. And that can cause some problems, as we'll discuss in the next video when we introduce factor analysis. Factor analysis is going to explicitly recognize that each of these components of the measurement system, or the M matrix, could be measured with error. And so we want to be able to separate what's measured with error versus what's correlated with each other that is redundant, that could be dimensionally reduced. So hopefully you've learned some things in this video, and I hope to see you in the next one as well.